Welcome to the 1965 Nobel Prize in Physics. This is a big one. Shared between three people, Sin-Itira Tomonaga, which I hope I pronounced that right, Julian Schwinger and Richard Feynman. I know I got those right. Richard Feynman is actually one of my favorite sort of scientists. If I had to pick sort of my, the rock star group of five, he's always in that list, but we'll get to him in a minute. So the official prize language for the shared prize was for their fundamental work in quantum electrodynamics with deep plowing consequences for the physics of elementary particles. That's the way the Nobel Committee worded it. These three had very different approaches to this work. So they all contributed to it, but they contributed to it in much different ways, very significant ways in all cases. Now, what the heck is quantum electrodynamics? I've mentioned it on other videos, but just to make sure everybody's aware, quantum electrodynamics is relativistic quantum field theory of electrodynamics. So it's basically how's that interaction between a particle and a charged particle and an electric charge field or an electric charge interact. How does that happen? But in more extreme cases, but you're dealing with the quantum world and inside a relativistic framework. So we're not just talking about your everyday standard charged particles here. We're talking about in extreme circumstances. And for a while, this stuff didn't quite fit together. There were observations that didn't fit with theory. There were theories that didn't fit with observations. So a lot of work had to be done to clean it up. And much like string theory, I'm going to throw that in, quantum electrodynamics was almost abandoned at one point until these guys came along and kind of fixed it. So let's dive in and see what they did to kind of rescue this thing that was about to go away that is now sort of bread and butter for a lot of people. It's really important stuff. Stay tuned. Now, Tomonaga's work was vital for many, many, many reasons. But let's kind of go back to the beginning. After the acceptance of the theory of relativity, thank you, Professor Einstein in 1905 and his Nobel Prize in 1921, and especially when quantum mechanics was becoming more sort of mainstream, an initial set of early stage relativistic theory was developed to kind of explain that interaction between charged particles and electromagnetic fields. That theory didn't really work. It was sort of partially developed and was sort of due for either sort of upheaval or throwing it out instead of starting over. But his work, in particular, Tomonaga's work, helped really kind of save electrodynamics because it explains something called the Lamb shift. Now, the Lamb shift was first observed in 1947. And remember, the hydrogen atom was supposed to have just sort of one energy level. And what happened with the Lamb shift was they discovered a second one that was sort of similar to the first one. It sort of blended in at first, but they eventually figured it out. And it didn't fit with theory. It just was not fitting with the known theories at the time. So Tomonaga solved this problem in 1948 by using a renormalization process in mathematics, which heavily contributed to a new direction in quantum electrodynamics. Now, his work became important because he helped make quantum mechanics, quantum electrodynamics, consistent with relativity theory. And if you have a theory that doesn't fit with another more proven theory, you're kind of gone, right? You don't really work. He showed quantum electrodynamics does agree with these experimental results to a high level of accuracy. You can actually get the math right. Some people before him were missing some terms. They didn't quite get everything they needed to do, but he kicked it out. He knocked it out of the park. He solved that pesky Lamb shift problem that people were seeing in the lab, but the theorists couldn't quite get to work correctly. He developed some really basic principles inside quantum electrodynamics. And honestly, without him, and to a lesser extent, the other two on this project, or on this prize, but without his work, I really think he really served to rejuvenate the electrodynamic, the quantum electrodynamics enthusiasm, because it was about to be thrown away. So I think he was sort of vital in keeping it sort of at the front end of the theory groups. So thank you, Professor Tomonaga, for your work. And now let's move on to the next of this trio. So one of the things I find interesting about being a physicist is there's not a lot of us. I mean, you'll find some at universities, there's enough of them, but if you're working in a subdiscipline of physics, everybody at least knows everybody's name, work, they're familiar with each other, at least to a certain extent. Maybe not everybody, but it's not a big world. So Julian Schwinger was the second of these three. Now, he got his PhD under a guy named Isidor Rabi, who won the Nobel Prize in 1944. It's on my playlist. You should check it out. Julian Schwinger did some work on the metallurgy part of the Manhattan Project. So he didn't really work directly in Los Alamos. I think he worked at University of Chicago at the time, working on some of the metallurgical aspects of the project. But he did work directly with Oppenheimer at Caltech from 1939 to 1941. So he had sort of a foot in that world. So all these guys were, sort of all knew each other. Now, his work in the quantum electrodynamic case was driven partly because the electron's magnetic moment had been shown experimentally to be somewhat larger than was expected by the theory, and the theory had to be reformulated. So Julian Schwinger came along in 1948. He went through a process again known as renormalization, and he significantly contributed to fixing that mathematical problem and advancing the field of quantum electrodynamics a little bit further. Now, his work became important because he really did, from 1947 through 1953, work to kind of fix that problem with the magnetic moment, and ultimately did. He also helped them use that same set of mathematics to overcome other more recent lab experiments that just weren't fitting with the known theories. So he used his work to sort of say, those lab experiments weren't wrong. Those experimentalists got it right. Here's how we explain it mathematically. Now, his source material, his work, his theory has been used as a general approach to deal with many other physical phenomena since that time. Things like photons are much better described using his work. Gravitons, which are thought to be gravity particles, have never been detected yet, but maybe someday. Strongly interacting particles, a lot of nuclear physics, a lot of these weird little things are explained by his work. Now, he even proposed an effect which describes and has actually been proven to very accurately describe how an electric field can pull electron-positron pairs out of a vacuum, which is a whole hour-long discussion all by itself. But it was revolutionary stuff. He developed the first sort of electroweak theory. Now, some of his techniques, such as quantum action principle and the proper time methods, are commonly used tools throughout physics. So his influence is felt in labs all around the world, even today. So let's dive into who honestly is kind of one of my favorite theoretical physicists. Yeah, Richard Feynman. Surely you must be joking. Mr. Feynman is a pretty good book. Check it out if you get the chance. And I do highly recommend finding a story that's been told, and actually a recording of it where Richard Feynman was telling the story. Somebody recorded him telling it, that he used to have this weird hobby. He'd get bored easily, so he'd find ways to keep himself entertained. And there's one here running around on YouTube about his hobby of safe cracking, which he thought was a lot of fun to go do. And there's a story about him, told by him, about how he used to crack safes while he was working on the Manhattan Project, and one time cracked one that held all the secrets of how to build a nuclear weapon, just because he didn't want to wait while somebody else showed up to unlock it. He wanted to get back to work. Not highly recommended if you hold a security clearance to do that sort of thing. That'll get you in a lot of trouble and get other people in trouble too. So I wouldn't recommend it, because it turns out security people have very little sense of humor. Now, Feynman's contribution to electrodynamics was really the introduction. What he won the prize for was really the introduction of the Feynman diagram. These are really easy graphical representation methods to show how that interaction between particles, and the diagrams themselves simplify that calculation of intersection of probabilities. So they really are just how to take this really complex subject and make it into one simple diagram so that you can kind of understand it and not have to go through a whole bunch of an hour-long process to really kind of figure out what's going on. You could do it in minutes. And Feynman diagrams themselves offer a very clear picture of particle interactions in space-time. They are consistent with the laws of quantum mechanics and special relativity, and they actually were used for the fundamental development of string theory as well as M theory, which again are completely more complex subjects we'll get to someday. Now, his lectures, one of the things he was famous for was he was one of those guys that was just amazingly good at taking shockingly complex subjects and making it so that anybody can understand it. He was very good at taking those things and sort of making it so the layperson could understand it, and still doing the graduate level seminar on it as well. So he could go either direction, where he could go incredibly complicated or he can go incredibly simple. He was sort of the master at doing that. And that's one of the things that I think more scientists should strive for in their career, is the ability to explain these complex subjects to anybody with a PhD in the subject and 20 years experience like I've got. I can sit down and go teach a graduate seminar on the fields of physics that I've worked in. Not a problem. Now, is somebody off the street going to be plopped down in that room and understand what's going on? Absolutely not, because it's a crazy, weird, detailed level explanation of the whole thing. There's nothing wrong with that. It's just I've spent 20 years doing it. You plop me down in a commercial kitchen and have a chef try to explain to me what's going on, I'm going to be lost and hurt somebody. So, it goes both ways. It comes with experience and background and the stuff. Now, Feynman, and I think my goal and more people's goal should be able to say, hey, can we also take that complex subject and get my 14-year-old to understand it? Little bit more challenging thing to do. You may not understand the math, but can you understand conceptually what's going on and why it's doing what it's doing instead of just this is what it's doing, remember it, memorize it, move on. No, you want to understand why something is doing something in the nuclear world is doing what it's doing. And that was one of the gifts Feynman really had. He was so good at that. It's one of those things we should all strive to do better at. And I'm going to spend the rest of my career trying to get better at. So I do hope you've enjoyed this video, and we will see you on the next one. We're getting into some really cool stuff in these more recent prizes that'll have a lot more fun kind of application-oriented space for what's going on. But Feynman, if you have not seen some of his lectures, look him up on YouTube. They're a blast. Please don't forget to click the like and subscribe button. It really does help out with the algorithms, and we will see you on the next one.